Howdy class. For anyone who is new to our lecture, this is a reminder slide that I've given many times for the people who have been here from the beginning, so I apologize to them. But new people, contact information for myself and for our IA and SI leader. So that's Nick is our IA, he's a graduate student, and Austin Bond is our SI leader, and he is an undergrad like you guys, but he has successfully completed Chem 119 and is going to give you tips on how he did it during his SI sessions. So here's our contact information. These are my office hours, and Nick and Austin's review sessions are posted, the times that they occur, and the links are posted on eCampus for you. Reminders, labs start next week, so we can finally start talking about labs soon. You still don't need to buy anything until then. We'll go over it in the first lab meeting, and then you can get into the site. If you are new to the class, make sure you go on our site on eCampus, look at my syllabus and these other documents for getting started to switch your ALEKS from a different Chem 119 professor and to join my REEF class instead of the previous lecture professor if you came from somewhere else in 119. Or just to make your own just to do these for the first time if you are new to Chem 119 and just decided to add it for fun this semester. There's an introduction assignment that is on eCampus under participation questions, and that's going to be due tomorrow anytime you go to eCampus. You go to the menu on the side, click on participation questions, and it's the first thing in there. You click on the actual words introduction assignment, and it opens a new window where you will be able to attach your document. All right, and just to review, if you are new, there was homework due on Sunday and on Tuesday, and there's going to be homework due tonight. So if you are new to the class, you will need to do those, but they are currently closed, so you'll have to send me an email so I can reopen it for you. All right, let's start the new stuff. All right, so we're going to talk about energy and energy changes. We're starting chapter 3. Energy corresponds to work being done on or by a system, or heat entering and leaving a system. We will learn more about that in chapter 10, where we learn this wonderful equation. E is equal to work, which is W, plus heat, which is Q. So all of the energy that is in a system comes from the work that was done on the system or the work that it's doing on something else, and the heat that is entering or leaving the system. That's all the energy is related to those two things. But you don't need to worry about that for now. For now, you just need to worry about these two types of energy, kinetic energy and potential energy. This is the energy basics. So kinetic energy deals with motion. It's got a little K to denote that it's kinetic energy, and you might see V or U for velocity. I like the V, but your textbook likes the U, so we might use them interchangeably. I like V because velocity starts with a V, but there are other things that we like to call V in chemistry, and it gets confusing. So U is a little easier maybe. And the energy is equal to 1/2 times the mass of the object, m, times the velocity squared. So m is the mass of the object, v is the velocity, and you want to square it. So 1/2 mv or 1/2 mu squared. And the type of kinetic energy that chemists care the most about is not really how much energy it takes to kick a soccer ball, or how much energy it takes to throw a baseball. We don't really care about that in chemistry, but we do care about thermal energy. And thermal energy is the energy caused by atomic and molecular motion. So that is motion on a really, really tiny scale, just like everything else that we study in chemistry. And that motion creates heat, which we call thermal energy. All right, there's also potential energy, and potential energy comes from the position of the object. I like to think of it as the potential for motion. So this object is not moving yet, but it has potential for motion, like the energy that's required to hold an object at a certain height. So you are not throwing the object or pushing it or anything, you're just holding it, and your energy is counteracting the force of gravity. So that is the potential energy, how much energy it takes to hold an object at a certain height. Because the potential is that if you dropped it, it would move and it would fall thanks to gravity. That's how I like to think about potential energy. And chemists study two types of potential energy. We don't care about dropping things from certain heights, though that's pretty cool, but that's more of a physics thing. We care about electrostatic and chemical energy. So chemical energy is stored in chemical bonds, and that's going to come up again in chapter 10 when we talk about energy and thermodynamics. So we don't need to worry about chemical energy for now. But electrostatic energy, we have already seen, even though you might not know it. Electrostatic energy corresponds to the energy between charged particles, like how we said before, and how people say all the time, opposites attract. That doesn't really take into account the other part of that, where like things repel each other. So two positive charges don't like to be near each other, or two negative charges don't like to be near each other. That is also part of electrostatic energy, not just opposites attract. So it's the energy between charged particles, and it is based on Coulomb's law, which I've mentioned before, but now we're going to get the equation for Coulomb's law. This isn't quite the equation. There's a little bit more math typically involved, but this is the simple version. That's why this is a proportional sign and not an equal sign. But the energy, the electrostatic energy of a system is proportional to the product of the charges divided by the distance between the charges. So if we have a particle that has a +1 charge and a particle that has a -1 charge, and they're one distance unit away, depends what you're talking about, probably nanometers or picometers, because charged ions are really small. There we go. I'll call it 1 nanometer, but basically 1, whatever. We're talking about relative numbers really and not actual numbers, so it doesn't matter. So that energy is going to be negative. Positive times a negative equals a negative. So when energy is negative, that is an attraction. Oops, can't spell attraction, sorry. When energy is negative, that's an attraction. Essentially, think of that as the energy decreases. They want to be closer together, so that you don't need as much energy to hold them apart. The energy decreases so that they move apart. They move together on their own. So negative goes with attraction, positive goes with repulsion. So this is when we have two like signs. This is when we have +1 and +1, or -1 and -1. That will end up with a positive electrostatic energy, which means there's repulsion in the system. And you guys are going to look a little bit more about this in your homework. You're going to be studying relative, the relative electrostatic energies of different systems, how they compare to each other, and seeing a little bit more of this equation in action. So as you can see, it's the product of the charges. So The bigger the magnitude of the charges, the bigger the energy, whether it's positive or negative, because two bigger things multiplied by each other equals a bigger product. And it's inversely related to the distance. So as the distance increases, the energy required to hold those particles apart from each other goes down. So when Q goes up, E goes up. When D goes up, E goes down. Got it? Awesome. So just so you know, potential energy can be converted into kinetic energy and vice versa. For example, kinetic thermal energy in these atoms and molecules can be converted into potential energy when we form or break a chemical bond. So we have atoms bouncing around in a system, and all of a sudden they come into contact with each other. So they had kinetic energy, which was making them move around, but now when they come into contact with each other, they might form a chemical bond, and then the bond has potential energy. So energy can only change between different forms. It cannot be created or destroyed. We can have potential energy become kinetic energy or vice versa. We can have light energy become heat energy, become motion energy, whatever. But it can't be created or destroyed. Whatever energy you start with, if it goes into a different system, the other system is going to get the exact same energy that left the first system. That is the law of conservation of energy. That's very important. Remember that. All right, and just so you know, because there are many forms of energy, there's also different units for energy. Joules is the SI unit for energy, so that's the one we'll be using the most. British thermal units you might have heard of when you're looking at heaters or air conditioners. And calories. So there are two types of calories, to be more specific. Calories with a little c is a more chemistry focused unit. Food calories, the ones that you're more familiar with, those are actually equal to a kilocal. So that's down here. I'll talk about that next. 1 joule. So what is a joule? It's equal to the energy required to accelerate an object using a force of 1 Newton over a distance of 1 meter. And that's great. What's a Newton? So if we break it down, joules are equal to kilograms times meter squared over second squared. So meters per second squared is our acceleration part of that sentence. There's another meter, so it's over a distance of 1 meter. So the distance of the meter. And we're moving a 1 kilogram object. So we're accelerating at 1 meter per second over the distance of 1 meter, a 1 kilogram object. Your textbook tells you a little bit more about how it's related to the kinetic energy equation. So I will let you read about that. A calorie, however, has a very specific definition, which will come into play a lot more in chapter 10. The 1 calorie is the energy needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. So that's very, very specific things you don't need to memorize now, but you will need to know about later. So 1 gram of pure water raised its temperature by 1 degree Celsius. The energy to do that is 1 calorie. That's the definition of a calorie. And a food calorie, the one you're more familiar with, is actually equal to 1,000 of those basic calories. So we denote the difference between those two with a positive, or sorry, not positive, a capital C for food calories and a lowercase c for the other type of calorie. So this should be a lowercase c. I just started a sentence with it and I wanted it to be capitalized, but it shouldn't be. Cool. All right. Let's look at a little practice problem that's similar to your homework before we go on to the next section. So we want to decide how objects in the table would be listed if they're listed in the order of increasing kinetic energy. So we want to remember our kinetic energy equation is 1/2 mv or u squared. So that's our velocity. So we've got 56 gram mass, 14 gram mass, 14 gram mass, 18 gram mass, and we've got different velocities. So let's see how they relate. Okay, so it looks to me like 6.2 is the highest speed. So I'm going to look at speed first. So these three all have 6.2 meters per second as their speed. So they're faster, and energy goes up when velocity goes up. So they're going to have more energy than this one, most likely. But let's look at the masses now. So the masses, our smallest mass is 14. So this guy right here is the smallest mass and the smallest velocity. So he's going to have the smallest energy. So he's number 1. Knocked that out right away. All right, so next, the other 3 all have the same velocity, so we only have to look at the mass. So 14 grams is smaller than 56 and 82, so we have a higher speed than the first one, but a smaller mass than the rest. So this one's number 2. And then 56 is less than 82, moving at the same velocity. So that's number 3. And finally, number 4, the highest kinetic energy is the one with the most mass, big mass, and big velocity. It's moving very fast. Okay, cool. So that's it for 3.1. I'll start another video for 3.2.